In this online lecture, I'm going to introduce you to the mass spec machine. We're going to talk about how it works and roughly how to read the data. And what are our key points here? Number one, we're going to see that the mass spectrometer can provide the molecular weight of a compound. Usually the highest value, MZ peak, is the molecular ion peak. We're going to make sense of that. We're also going to make sense of this. Number two, the mass spectrometer can fragment a molecule, and some fragments appear on the mass spectrum. The most abundant fragment gives rise to what's called the base peak. So, let's talk about this then. Let's say, for instance, we find some substance somewhere and we don't know what it is. And let's pretend it happens to be propane. And if we're trying to find out what the substance is, a good place to start would be, what is the molecular weight of the compound? So we take our unknown mystery substance here and we stick it in the mass spectrometer. Now, let's pay attention to something really close here. All right, remember this is a CH bond, and let's talk about the different types of electrons that are present here. Remember, carbon has 6 electrons total. Some of those electrons are what's called, remember, his core electrons. These are simply the electrons around carbon that are not involved in a bond. And the other type of electrons, of course, are these electrons right here. These would be the bonding electrons. So for the mass spec, we like to distinguish core electrons from bonding electrons. And let's see why here. Let's go back to our situation here. And what we're learning here is that when we stick a molecule in the mass spectrometer, what we end up doing is shooting an electron beam at the molecule. Think of it as almost taking like a gun and shooting an electron gun at the molecule. And let's go back to our situation right here. And let's focus up close here. Let's say this is our electron beam, and by random chance here, let's look at this situation. The electron beam happens to shoot one of the electrons, in this case the core electron, and in the process dislodges it like that. Almost like playing pool, one of the electrons in the electron beam knocks out one of the core electrons. Let's pretend that happened in this case right here. If it does, then think about what that would create. It would create what's called a molecular ion. Think about it. If we dislodged one of the electrons from this molecule, propane, then the overall charge of the molecule would now be plus. Because remember, the molecule started out as neutral, which means all of the protons and all the electrons were equal. And since we dislodged an electron, he now has one more proton than he has electrons. But notice we're also calling this a radical cation. Again, since we dislodged one electron, he would therefore have one unpaired electron. So he ends up being both a cation and a radical. Now, what we do at this point is we take that molecule and we accelerate it through a magnet. And on the other side of the magnet, we have something called a detector. And he does exactly what you would think he does. He detects substances. Now, without getting crazy with all the physics here, you're just going to have to accept my word for it. When you move a charged particle through a magnet, it takes on a curved path. So our particle is going to curve like this. And it's going to hit the detector at a certain location. And wherever it lands, that enables the detector to measure the radius of that curve. Now, why is that so important to calculate the radius of curvature here? Well, let's just look at some physics here. Remember, if something's moving in a circle, it has a centripetal force. And what's causing the centripetal force here is the magnetic force being applied by the magnet. So in physics, we would say that the Fm, the magnetic force, is equal to the centripetal force. And let's expand these two equations out. The magnetic force is equal to Q, charge, times velocity, times B, the magnetic field. And centripetal force is the same thing as mv squared over r. Notice we have v's on both sides of the equation, so one of the v's cancels out, and now we have this equation. And then let's do a little algebra here and solve this equation for r. Notice what we have here. This equation has m in it, mass, and of course it has the r over here. Which means if we could find r and then plug it into this equation, we can solve for m. provided we know everything else in this equation, and that is V, Q, and B. And let's just for now pretend that we do. If you haven't taken physics, don't worry so much about all this math here. Just know that there's a relationship between the radius of curvature of this particle and the mass. Now, how does the mass spec take this data and report it? Well, let's look at that right here. What the mass spec gives is a graph. And on that graph, on the y-axis, is something called relative abundance. We'll talk about that more in a minute here. On the x-axis is the m over q ratio. And notice in the upper right here in our equation, r equals m over q times v over b. And again, we said that since the detector measured the r value, we're able to solve for that m over q value. And that m is simply the mass. Which means if we stuck our propane molecule in the mass spec, we should see a signal at 44. And why is that? Simply because propane has a molecular weight of 44 grams per mole. And remember, this was the fragment that went through the mass spec that was detected by the detector. He so happens to have a molecular weight of 44 grams per mole. So notice, big picture here. We're taking a substance, we're shooting an electron beam at it, it's creating a molecular ion. That molecular ion is being shoved through two magnets, and it takes on a curved path. The detector measures that curved path, which in turn measures R, and knowing R gives us m mass. So seeing a signal here at the 44 mark means that the mass spec detected a charged substance that happens to weigh 44 grams per mole. Now, what about this relative abundance on the y-axis? Well, let's go back to our situation right here. Remember, when we're running a sample through the mass spec, you're not just putting one molecule into the mass spectrometer, you're putting, let's say, a whole mole. So imagine if this process continues. If we put a whole mole of propane and we keep shooting an electron beam at it, and that charged substance goes through the magnet and curves its pathway, we will get a signal at 44. But since we have, let's say again, a whole mole of it, then this keeps happening over and over again for a lot of molecules. So we're getting a lot of these substances, and each time we get one, that peak at 44 gets higher and higher and higher. And think about what that term means, relative abundance. The more abundant that charged species is, the higher the peak. So again, if we're running a big sample here, we should expect to see a pretty high peak at the 44 level. And again, that peak is due to this substance right here. Now remember, we're getting this substance if the electron beam happens to dislodge a core electron. But remember, there's other types of electrons in this molecule. So let's go back to our mass spec right here. And again, let's say we put propane into it. And of course, shoot our electron beam at the molecule. Let's see what would happen if our electron beam dislodges one of the, remember, bonding electrons. So, just like in pool again, we shoot an electron, it hits one of those bonding electrons and dislodges it. Look at the result here. You get a carbocation and you get the hydrogen with that extra electron there. So, this is what happens if our electron beam happens to hit a bonding electron. Remember, when we shoot the electron beam at the molecule in the mass spec, both of these situations are possible. That is, hitting a core electron or hitting a bonding electron. And remember, since we're putting a whole bunch of these samples in the mass spec, each molecule is technically, quote-unquote, breaking differently. That is, some core electrons are being knocked out, some bonding electrons are being knocked out. It's all by random chance, and all we're studying here is the possible ways that this quote-unquote cookie can crumble. So let's go back to our machine here, and let's say again we put it into the mass spec, but this time our electron beam dislodges an electron in the same way that we just saw. Remember, what we ended up getting there was a carbocation and a hydrogen with an electron. Now remember, the next step in this process is these substances go through the magnet. But let's look at the hydrogen first. Remember, hydrogen has one proton, and in this case he has his one electron. That means that this substance is neutral. And since he's not charged, when he flows through that magnet, he's going to take on a straight pathway. Remember, only charged particles take on a curved pathway between a magnet. so the detector would not detect him. But the carbocation is another story. He is positively charged. So when he flows through the magnet, he will take on a curved pathway. And again, the detector will measure his radius of curvature. And with that particular R solving for mass, notice this species would have a molecular weight of 43 grams per mole. It would be one less than propane because simply this molecule is one hydrogen less than propane. So let's look at this here then. Let's take our propane and let's spread him out so we can see all his bonds. What we just saw here is that one possible fate in the mass spec is breaking this bond right here. And again, creating a carbocation, which would create this substance right here, which in the world of mass spec is called a fragment. Think of that term for a second here. What we're doing again, we're taking propane and we're breaking it, and this is the fragment that's left behind. But that's not the only possibility here. Remember, there are other bonds in this molecule. It is possible that the electron beam could dislodge one of the electrons in this bond right here between these two carbons. If that happens, then remember, one species gets the positive charge and the other one gets the electron. And let's say this happens to be the case. Now remember, which one of these fragments is going to be detected by the mass spec? Of course, remember, it's the one that's charged, this one. However, this methyl right here with this extra electron doesn't have a charge. So he would go straight through the magnets and not be detected by the detector. Which means, again, the fragment that has the carbocation would be detected, and he happens to be a fragment that weighs 28 grams per mole. But remember, that's just one possibility. The other option is, remember, the electron beam could shoot this bond right here, dislodge an electron, but now by random chance the opposite happens, meaning the electron jumps up on the carbon to the left, and the carbon on the right becomes the carbocation. And again, remember, it is this species right here that will be detected, and this species here would not be detected. And it just so happens that this carbocation fragment happens to weigh 15 grams per mole. Again, look what we're doing here. We're just simply studying the way that propane can fragment or break up. What does this all mean to us? Well, let's go back to the spectrum here that the mass spec would spit out. Remember, we know that we would see the molecular ion peak at 44, but what we're learning here is that it's possible that we would see peaks for these fragments. For instance, the top one there weighing 43 grams per mole, you would actually see a peak at 43. And what about the second one there, the one that weighs 28 grams per mole? We should expect to see a peak at 28. And lastly, that methyl carbocation weighing 15, we should see a peak at 15 as well. So notice the data here is showing not only what's called the molecular ion peak, but it's also showing all the possible fragment peaks. So think about this for a second. The peak that has the highest value, in this case 44, we can assume must be the molecule when it's most intact, or very little has fragmented. So the 44 value is most likely the molecular weight of the compound. And we just saw that that heaviest peak is called the molecular ion peak. So that's why he's important. But there's another term we should also know. Let's look at the tallest peak on this spectrum. That is on the y-axis, tallest. This peak right here is called the base peak. Remember, this peak is due to that substance in the green box there. And notice that carbocation just so happens to be a secondary carbocation. What we're seeing here is that out of all the fragments, he should be the most abundant. Why is that? Well, let's look at the other peak here, the blue one here. Remember, that's due to this substance right here in the blue box. He happens to be a primary carbocation. And remember your carbocation stability, secondaries are more stable than primary. So it's more likely that we would get the fragment in the green box over the blue box. And he would therefore be more abundant, hence he should appear as a very tall peak on our spectrum. So what we're saying here is that the base peak on the mass spectrum is usually due to the most stable fragment. And therefore, it should also make sense that the last fragment here, the methyl, should be the least abundant peak. Because remember, methyl radicals are not very stable at all. On the real mass spectrum, you might not even see anything at level 15. So this would simply be the mass spectrum of propane. Let's just pause here for a second. I want to make sure you know something. You might be listening to this or watching it and saying, hey, you know, that's great, but what the heck is my teacher going to ask me about something like this? Well, we'll get to that. For right now, just simply understand how the machine works and how it spits out the data. We'll look at many practice problems as we move through this section. In fact, let's look at our first sample problem right here. Notice this question is asking you which spectrum below corresponds to pentane and which one would be 2-methylbutane. So, of course, what we're doing is taking pentane, putting it in the mass spec, and we're taking 2-methylbutane, and we're getting obviously two spectrums, and we want to see which one is responsible for which. So let's look at our molecules here. We got pentane, 5-carbon long chain, and we got our 2-methylbutane that looks like this. Now look at our mass spectrums here. Both have the heaviest peak at 72. And notice if you calculated the molecular weight of pentane, he would happen to be 72 grams per mole. But notice that would be the same molecular weight as 2-methylbutane. So the molecular ion peak in these spectrums are not going to help us. However, notice we do have something different here. We do have peaks at 57 in both spectrums, but one of them has a higher relative abundance and the other one has a lower relative abundance. Let's look at our molecules here and see which one might have a higher relative abundance at the 57 peak. Let's do some math here. Let's start with the pentane. 72 minus the 57 means that the molecule lost something that weighs 15. And think about it. What weighs 15? Well, a methyl would weigh 15. So think about this. What we're trying to figure out here is which molecule is more likely to lose a methyl upon fragmentation. Well, let's investigate pentane first. We can shoot an electron beam and break the bond between that first carbon and the second carbon, and he could possibly lose a methyl. And notice the carbocation on the right-hand side of that molecule, that would be detected by the mass spec, and we should see a peak at 57. Now let's look at the 2-methylbutane. Again, we could shoot an electron beam, and most likely this would be the methyl that is broken off. Why is that? Well, the resulting species would look like this, making the bottom species detected by the mass spec, and therefore giving a peak at 57. Notice if we broke this bond, we would get a secondary carbocation. For pentane, when we do this type of fragmentation, we end up getting a primary carbocation. Notice if you investigated this pentane molecule further, no matter how you cut up these bonds, you're always going to get some kind of primary carbocation. You could never get a secondary carbocation. However, with 2-methylbutane, we just saw it's possible to lose a methyl and get a secondary carbocation. So that means the first spectrum here with the high relative abundance at 57 must be the spectrum for 2-methylbutane, and the one on the right must be the spectrum for pentane. Again, because we would expect to see a pretty high relative abundance at 57 for 2-methylbutane and not so much for pentane. So this is one type of question that you could encounter on an exam. So what did we learn here? Key points. We saw that number 1, the mass spectrum can provide the molecular weight of a compound. And usually the highest value MZ peak, that is the heaviest peak, is called the molecular ion peak and is most likely due to the molecule in its most intact form. And number 2 here, we saw that the mass spectrometer can fragment a molecule, and some of those fragments can actually appear on the mass spec. And the most abundant of fragment gives rise to the tallest peak, which is called the base peak. And that base peak is usually due to the most stable fragment.